So far, we've learned how to evaluate limits for points on a line. Now we're going to build on that knowledge and look at a calculus technique called differentiation. In differentiation, we use our knowledge of limits to calculate the derivative of a function in order to determine the rate of change at an individual point on its line. So here's a function and its graph. Now we know that we can find the slope for a section of the graph by choosing 2 points and creating a straight secant line between them. To calculate the slope of the secant line, we divide delta y by delta x, which is really just a fancy way of saying we divide the difference in the y values by the difference in the x values. Now let's think about this for a second. Delta x is just the distance between the x values for the 2 points. Now sometimes we call this h, and if we know this value, we can rewrite our slope equation like this. Delta y is the difference between f of x plus h and f of x, and delta x is just h. So how does all of this help us measure our slope at an individual point? Well, suppose we move that second point so that it becomes infinitesimally closer to the first point. This reduces our h value to as close to 0 as we can make it. Now if we draw a line through the points, they're so close that on the graph they form a tiny straight line, and it extends to a tangent from the curve. So how do we calculate a point that's infinitesimally close? Well, we know that that's a limit, and in this case, it's the limit of the slope equation as h approaches 0. This whole formula calculates what's known as the derivative of the function. Let's put it to the test. Suppose we want to find the slope or derivative at the point where x is 3. We can substitute 3 into our derivative function. Now we know that the function f encapsulates x squared plus 1, so we can incorporate that into the equation for our x value of 3. Now on the left we can factor out the perfect square as a squared plus b squared plus 2ab, and on the right 3 squared is 9. Now we can consolidate the like terms, so 9 plus 1 is 10, and 10 minus 10 cancels out, leaving us with h squared plus 6h over h. Well, h squared divided by h is just h, and 6h divided by h is 6, so our limit as h approaches 0 is h plus 6. And of course if h is 0, then our derivative for f of 3 is simply 6. So the slope at the point where x is 3 is 6. Now let's see if that looks right. Here's the tangent line that passes through the point where x is 3, and sure enough, for each unit along x, we go up 6 units on y.